Okay, previously we stopped at example 8. Today we learn about relative analysis on acceleration. So as you can see, this dump truck, we have a reference axis x, y. So to do this dumping action, the piston point A to point B will be extended, and there's a change of angle of this this dustbin here, right? So you're familiar with VA to VB and so on. So this is the previous equation that you're familiar with. We change velocity into acceleration, right? So VA equal to VB equal to VA plus VA stroke A. What I mean by VB stroke A means position of B from A. And acceleration, you can break your acceleration of relative acceleration, you can break into normal and tangent direction, right? So let's say we have a object, right? So this link was rotate with angular velocity clockwise and angular acceleration clockwise. It is positive or negative direction. Yes. Why negative? Huh? What's your you should use your right hand rules, right? So what's your thumb tell you? Go in or go up? Pointing. Point, where does it point? It point into the screen or outside? Point outside the screen. It point like this or point like this? It's in. So you have a negative K. All right, so this one, when point A and point B rotate this way, so this link, point A will move in the collinear motion because it's rotate like this. So you move in collinear motion, and your acceleration of point A, there's a vector. So when you have a collinear motion, you have two vector. One is tangent, one is normal. You combine tangent normal, you get one resultant. Okay, same with point B here. Point B rotate clockwise, so also move in a collinear motion. So you also have tangent and normal direction. You combine these two, you get resultant of acceleration point B. So this is a general plane motion. What I mean by general plane motion? You have two motion, which is translation and rotation. So translation means point A, point B move in the straight line, and then you fix at one point and then you turn. Okay, so general plane, if this come up in the question later, you need to split the final action into translation and rotation. So when you have a rotation at point A, you need to use the relative vector, where you log point A, look to B, you get RB stroke A. RB stroke A, you will have, if you look at point A, from point A, your acceleration will have two magnitude. One is tangent, one is normal. Then you combine these two, you will get the resultant. From here also, you can find the angle. Angle from here. Okay. All right. Okay, you should able to draw this vector diagram from here. I'm not going deep into vector, right? You're already expert already, so I'm not going to go deep there. So same with this action. So we have given this mechanism. So A linked to B, B linked to C. You are given the action as clockwise. What is how point C move? To the right. How point B move? Go down in the collinear motion. How point A move? Huh? It doesn't move, but what action it have? We have a fixed location with a rotation. Right. Now, this diagram, you should able to draw the motion diagram or kinetic diagram, right? So you look AB first. AB, you draw kinetic diagram. You focus on this arm only. So B, rotate clockwise. You have a tangent acceleration direction and normal direction acceleration. You square tangent plus square normal square root, you get resultant. Okay. Again, recall when you go into angular motion, your normal direction is minus W square R. In this case, you're looking at B stroke R, so your R is B stroke A. Okay. Same with tangent. Your tangent is alpha R. It must alpha cross R. Okay. So this one you should already memorize in your brain already. Yeah? I will not repeat this one. Okay. You combine the two. Previously, we discussed about the vector diagram. Acceleration B equal to acceleration A plus the resultant of your acceleration B stroke A. You break your B stroke A acceleration into tangent and normal direction. Okay. Why negative there? They're not positive. Why? Why negative? Why negative? Where is your R positive direction? Huh? Huh? Your R, where is R positive? Go in or go out? Go out, right? Yes, correct. That's why we use negative. Understand? Yeah, okay. So now, if your disc was rotating and you start to see the gravitational point or central of mass point, right? So when you look at the diagram later in your test 2 or final exam, when you start to see G point or center of mass point on the diagram, it is fall under chapter 5 onwards. Huh? So you need to consider it from the gravitational effect from the center of mass. So this will rotate from G point around the G point and in the clockwise direction. So where does the thumb tell you? Go in or go out? The omega clockwise. So it's going in. Huh? Right. So your kinetic diagram, if you refer to point G, if this one rotate in this way, this object going to move to the right, right? So if you're focusing on point G, your G move to the right, right? So your velocity G pointing to the right. And if you're referring to point A, right? You're standing from A, look at a G, RG stroke A means you're looking from A, arrow pointing to the G. So how you find velocity? Velocity equal to velocity G equal to VA plus omega cross R, G stroke A. Okay, so this is in vector form, right? So VA here, A at the point here do not move, so 0, omega negative going in, cross R, R, G stroke A is going up, so that's why it's a positive J here. J, K cross J, right? So you know that your Vg, how you calculate Vg in scalar form? Omega R. You time differentiate it, it become acceleration. You get acceleration from the center of mass is alpha R. Okay. What is this slight different from the previous one? You start to see the G point, center of mass. Previous 5.1 until 5.6, there's no G point there. We're only interested in point A and B on the same body. But today, this session, you start to see center of mass G on the question or on the assessment, right? Okay. Now let's look at block AB, right? Okay. Have we gone through this one? Not yet. Okay. So AB was confined to move along inclined plane AB. So point A move here, point B will move 45 degree. So if A move down, what happened to B? Move up, huh? Right. So when A move down, B move up, what is the rotation? What is the angular motion? Anticlockwise, and it is going in, huh? Right. So here you already fix your angle already. Your V fixed already. Although you see a round body here, but there's no tangent direction, there's no normal direction because it's a straight surface with 45 degree, right? You are given point A accelerate at 3 meter per second square, velocity is given. VA, acceleration A was given. This is not angular dimension. You need to link V equal to omega R. A split into two components. A, this one is the resultant. You need to split into tangent and normal direction. Okay. So there are two analyses. First step, you use vector analysis where you convert all the vector into I, J, and K. Okay. So kinetic diagram. You convert this kinetic diagram. You draw the body first, AB, because you're more interested in point A and B. You draw the body. You include the information given, or you expected the rotation or the angular motion. In this case, the blue arrow you add into the kinetic diagram. So it's in the anticlockwise direction, alpha and omega. Right? So at first you don't know point 2, you need to calculate. But you draw omega alpha arrow first. Then you can draw the velocity direction, 45 degree go down, and acceleration also. Right? Go down. So this one will go up. Right. Now, here it asks you to determine angular acceleration. So angular acceleration, so that's why in your kinematic diagram, you're seeing acceleration here and not velocity. Of course, the full set, you should include V over here. Okay, V at point A, V at point B, same. Right? But this question, example 9, asks you to focus on angular acceleration. So that's why you see A here. Write the acceleration equation. So I will not go back to show you how to find omega equal to 0.283. It's your homework. In radian per second clockwise. Right? There's a calculation there. Your homework, go and find. Then you have alpha and AB, you don't know. Acceleration at A was given, right? So you need to find alpha. You need to find AB. So acceleration equation given by this one, AB equal to AA plus alpha cross R minus omega square RB. You're looking at A, B, log A to B, sorry, B from A, yeah. So this is your R, B stroke A. You write in vector form, again, cheat code. Convert this one into acceleration, differentiate 2 times. You get this one become acceleration. This one break into normal tangent direction. Okay, so I'm not going back to this one already. That's why you see the equation on the screen here. Remember, it is negative and not positive. Right? Many students, when they come to test 2 or final exam, they will write this one positive. You break AB go up, right? 45 degree. You break into I and J, so that's why AB cos 45J plus sine 45J. Then A also same. Break this arrow into X and Y plus alpha. What is alpha? We don't know, but is going in, sorry, going out, positive. Okay, positive K cross R B stroke A, X direction. The length is 10, so 10I. Go home, do homework. When you take K cross I, what you get? Same, you do the omega. Omega was, you find 0.28 square, and R again 10I. Right? So you do the cross product and also equating, you put all the I together, you're able to find the missing piece. Okay. Right? So this is how you find using vector analysis. You can use another method, it's called scalar method, where the free body diagram and kinematic diagram look differently, totally differently from the previous one. So don't use vector diagram and you solve using scalar analysis. I'll put a question mark. Although you get the correct answer, you won't get marks for that because you don't know what you're doing. Okay, so always I will refer your answer to your free body diagram or kinematic diagram. So you change the rod AB into this form. So point A to point B, and at point B is go up and go to the left, and you have rotation over there. So you write AB equal to AA plus AB stroke A. Again, change B stroke A into tangent and normal direction. So you write AB equal to AB 45, you go up 45. A go down 45 at 3. At tangent acceleration, angular acceleration equal to alpha R. Tangent, and this one, tangent go up at B stroke A. The whole thing go up, all right? Then normal. B stroke A, you'll get omega R. Okay. You're going to the left. Here, equation positive. So it's again, it's a different if you use vector, it's different if you use scalar. Pick one method that you feel comfortable. Then here you have angle. Convert this equation in x direction and do one set for y direction. You can get the same answer. Okay. Your answer, again, you're learning engineering dynamics. Your answer always need to give direction. Example 10. You see point G already. A spool unveiled from the cord such instance show that angular velocity was given. Angular velocity is omega. Angular acceleration is alpha. Determine acceleration of point B. Here, clockwise, you are given G to point A is 0.2, G to B is 0.3. How you solve? How you solve? Again, you have two methods. Showing you the vector analysis. Draw the free body diagram. Your angular, not angular, acceleration of point G will go up or go down. Point G will go up or go down. Go down, huh? So AG equal to alpha R. Right, this one I don't need to go back already. We already become expert of this equation. A equal to alpha R. Substitute alpha given R from the diagram. Right, G to A, you get this acceleration of G point. You apply the acceleration equation to point G and B. Again, draw your kinematic diagram. From G to B, this one rotate this way, tangent this way, normal this way, or x, y, x this direction, y this direction. Right. So, and then your R, relative R, B from G point. Then AG go down. This one row go down. So AG go down. Apply your diagram, your acceleration equation. AB equal to AA plus alpha R minus omega square R, omega square R. Modify this equation. You are referring to G and B stroke G. You are interested between B and G and no longer A and B. Right? So again, in your assessment, your notation is important. If your free body diagram you do not draw, sorry, I put lots of question mark in your answer. I don't know what you are saying in your solution if you do not draw free body diagram or kinematic diagram. Yeah, and the question is very specific. Section 1, you are forced to draw free body diagram and kinematic diagram. If you don't do section A, I won't mark section B because sure you cannot do it. Okay. Break your AB into x and y, which you will see vector I and vector J. This one. Okay. So same with this one. Okay, y, x here, y here. This is a circular motion. You know that circular motion will go this way. You rotate right, tangent direction, go this way, right? So same, you do the same. G minus 0.8. If a question asks me now, don't later you come to consultation hour, you're going to ask the same question. Alpha, negative because going in. R equal to 0.3. Okay. 0.8. Where does your G point acceleration? The whole object G point go where? No, where is your G point after you release? Where does your G point go? No. Where's your G point? We are talking about A, not angular alpha. Acceleration. Don't confuse angular and normal acceleration. Yeah. Nika, if your question, ask now. Don't come and ask the same question during consultation hour. Okay, nah? So that's why acceleration go down. Minus 0.8 I. Okay. Alpha go in K minus K. R is 0.3 J. Same with omega. Omega square. What is your omega reading? What is omega magnitude? How many omega? What is your omega value? 3, huh? Okay. RB is 0.3 J. You do cross section, the cross product. Okay. So again, you get your x direction, y direction of acceleration. You need to find resultant. Find resultant, find angle. Okay. Right. Scalar analysis, same. Draw kinematic diagram. Different kinematic diagram. Vector analysis and scalar analysis, they are different approach. So if you draw scalar, you focus on the G point, look at the B, then predict what is B. As you can see, scalar, you look at circular motion. You have normal and tangent direction. Vector, you only see x direction, y direction. Okay, vector, you see I, J, K. Right? So analysis, scalar analysis, you see tangent and normal, or collinear motion, rectilinear motion. Right? So here you know that it's rotate in a circular motion. So you have A, T, and AG, but label clearly in your answer or free body diagram, you are referring from G to B. So here and here. Remember, your N is always pointing in a circular motion. Radius always from center going out. Okay. Write the normal vector diagram, vector equation. AB equal to AG plus AB stroke G. Convert B stroke G into normal tangent direction. Apply the equation. Right. B, acceleration at B, you break into X and Y. So here, Bx plus By. Right. Then your G going down again. Your BG tangent equal to alpha R. Tangent equal to alpha R. Alpha is 4. R is 3. Normal, 3 radian per second, 0.3. Okay, I put positive because I mark going in positive. If I point up, this one become negative. If I flip and write negative, my arrow is pointing up. Okay, because I want my answer in positive, I draw my arrow according to the motion. Solving, you get the answer for scalar. Same example 11. Example 11, crankshaft. Like what I showed you in the beginning. Point A to point B, rotate clockwise. What happened to point C? Point C will move up. This one will become straight. Here you see a non-conventional triangular. You see this shape, quickly call your cosine rules. Draw a rectangular, triangular, write cosine rules over there. Label ABC and all the angle as your reference, right? So you're given the angular velocity for link BC and AB. This one, you dissect, you do it slowly, one by one. You look at AB, analyze the velocity and acceleration for link AB first. Once you complete this one, carry forward the information for point B, continue to do for BC. Okay. Or you can do BC first, then work backward, AB. Same. So all the information given, determine acceleration of piston at the instant AB at the position so. At the instant, omega so and so, omega so and so. Acceleration of piston means this one. What is your C acceleration? So convert your diagram into kinematic diagram. Here, you draw XY means you are using vector diagram, a vector approach. So AC go along y-axis. And then you find the length from BC in horizontal. You have the length of BC. You have the angle. You can find BC vertical distance. Same with BA. You can find, you have an angle 45. You're able to find the vertical distance A to B. Okay. So again, acceleration equation. You break RB into XY direction. This is a vector. Vector break in Y and X direction. So your Y is positive, X is negative. Okay. Same with RC stroke B. What is RC stroke B? This is a vector, X and Y both positive with an angle. Okay, I will not go deep into a calculation. You're already expert already. All right. So once you have these two values, you start to look at rotation or angular motion. Same equation come out, alpha B equal to alpha A plus alpha A cross RB minus omega square R. This one, you look at crankshaft A to B. You look at this one first. After you do this one, you do this one. Alpha A, alpha B, you need to find. Alpha A 0, Y 0, because cannot move. Alpha AB, Y negative, Y alpha negative. Huh? What is alpha AB? Clockwise, huh? Right hand rules, go in, huh? That's Y negative K. RB, cross RB, you define already just now. RB. Okay. So omega square, again minus, then omega square 10 given, then RB again. RAB lah. It should be RAB, RAB, right? It's not. So that you know it's a same, right? So you get your acceleration at B point, at here. You have X direction, Y direction. Positive and negative, where's the direction? You have positive X, negative Y. Where is the direction of your acceleration? Yeah, where's the resultant? Here. Okay. So you having a general plane motion here. So you can use the relative motion C and B. You change this equation to link C and B. Okay, you want to find C, right? Put C here. B plus alpha BC cross RCB minus omega squared BC RCB. This one you want to find. The answer, the question asks you to find AC. This one you have. This one? Positive, negative. Why positive? Huh? What is your alpha? Huh? This one? So what is your right hand rule tell you? Okay, positive. RCB. This one. Minus omega BC was given. And RCB again. Put in I and J. You know that C is go up, so put in J. Put AB into IJ. You define just now. BC same. Alpha BC positive K. Go up. R also same. Omega also same. You solve, you get your BC anticlockwise. Okay, this one in alpha. Because the question asks you to find angular acceleration of the piston. Right? So you have this one, and you find alpha. Okay. Now we look at rotating axis. Previously, before 5.8 or 5.7, we only look at object and rotate. 5.8 onwards, you look at what happened to the axis. As you can see on the screen here, we have positive X, capital Y, and small x and y. This session, you start to see omega symbol in a dumbbell shape. This is acceleration, angular acceleration. But when you see this symbol, we are referring to the rotating axis and not the object. You're looking at the axis, reference axis rotation rather than the object. Okay, I'm not going deep into the derivation. This one, as your homework, you go and read. RBA equal to XBYB. RAB equal to X and Y. Okay, XB is the distance here, here to here, XB. Here to here is your YB. Okay. RB, how you link RB? There's a triangular here. What is the equation for this vector triangular? Okay. You have this one, right? Substitute this one over here. You get equation. Right. So again, we start to introduce you new symbol called dumbbell omega or omega. Same pronouns as this one, but this one is for object. This one is for axis. I'll not go deep into the derivation. You're going to read the slides. When there is a rotation on axis, you have one more vector looking at this. Is mathematics steps. Right. So again, I won't go deep into this. You go and read the slides. So when you rotate this axis, focus on this diagram. When you rotate this one, you will see this diagram. Okay. I enlarge this diagram. This is your rotating plane, X and Y. When your axis rotate at a certain angle, delta d theta, Y also rotate d theta. Okay. And your rotation omega is clockwise. Sorry, anti-clockwise. Okay. So where's the direction? So here to here, and we assume the distance from here to here is 1. Okay, here to here, your original I lah. When you rotate in a small angle, we assume this I prime also 1. Right? So when you have a small rotation, again, call back the small section of circle, S equal to R theta. Right? This one you run in your mathematics. So how to find the distance of this one? This one equal to I times d theta. You know that this is 1. So you do the mathematics steps. At the end, you do the derivation, you get this equation. Right. So I'll skip this one to read as a homework. At the end, I'm going to show you. At the end, the one that I highlight with red color, recall, this is what you learned before this. Because before this, you learn about alpha, omega, right? So here, if the rotation of axis, you have one new parameter added to the end, which is VB stroke A XYZ. Okay, just compare side by side, then there's one more need to add to the calculation. Okay. Same with acceleration. It's quite lengthy. This one is inside Canvas appendix. At the end, no choice, you have to memorize because we don't ask you the derivation steps. Memorize this one. If you're being asked relative motion analysis using rotating axis, memorize this one. AB equal to A plus omega dot cross RB plus omega cross bracket omega cross RB. You do the bracket first, then only you do the cross. How to do? Go back to your mathematics textbook, the cross products. Plus 2 omega plus VB stroke A XYZ plus A B stroke A XYZ. These two terms that I highlight with the blue line is called Coriolis acceleration. Okay. So this is what we showed you previously. When this one rotates clockwise, this is a general motion. It means it's a combination of translation plus rotation at point A. Right? Okay. How you know you need to use this equation? You look at a question. You have two objects. Previously, you only have one object, but 2 points on the same object. Here, you have axis, big X and small x. You have big XY, small xy, means this one, you need to use the equation that I showed you just now. So, at the instant theta 60 degree, rod angular velocity was given, angular acceleration was given, so omega alpha was given. At the same instant, color C, this one, when this one rotates 60 degree, you know gravitational force will pull this collar down. This collar move in the acceleration and velocity that you learn in your chapter 1, chapter 2. Okay, again, don't confuse between chapter 1, velocity, and chapter 5, angular velocity. Okay. So Okay, then you have a Coriolis acceleration. So here, determine Coriolis acceleration and velocity acceleration of the collar at this instant. So again, I won't go deep this one. You memorize the velocity equation for relative rotation of axis, because when you see xy, you use this equation. VB equal to VA plus omega cross RB stroke A plus VB stroke A XYZ. Okay, this one you memorize. Acceleration equation also same, you memorize. It's quite lengthy, it won't given in the exam. You modify accordingly. You're looking at C to O. So always your target is C because the question asks you at collar. Your target always outside the equation, which is on the left. You modify B to C, A to O. Okay, same with the acceleration equation. Okay, the rest, you read from the diagram, substitute, and you get the answer. Okay, so you're referring to a table. This one, you're referring to the table. Velocity at O cannot move, 0. Acceleration, since O cannot move, so no acceleration, 0. Omega was given, minus K. Why minus K? Your thumb pointing in. Omega dot, with its acceleration, also negative because pointing in, your right hand rules. Motion of C with respect to the motion moving reference, R C stroke O is 0.2 I here. So this is X. Right, from the origin O, it is a small changing or translating axis. So your R of your C from O is 0.2 I because it's moved in X direction. Velocity you are given also along small x direction, so 2I along x direction, so I. Acceleration also given along I also, so 3I. It's given in the diagram. Okay, so you have a small x and big X here. So don't confuse between the big X. You are not focusing on the small x, but small xy. Okay. So Coriolis acceleration is defined in the derivation steps equal to 2 omega cross V C stroke A of your x, small x, y, z axis. So you put in 2 omega from table just now. VC stroke A also from table. You substitute, you get the answer. And you do calculation, substitute this one, substitute this one, substitute this one, substitute this one. You get the answer. Huh? Same with this one. Okay. Last example. You have two planes from origin 400 kilometer. B move in a collinear motion, but clockwise. Collinear motion 600 kilometer in y-axis, but acceleration is in this direction. Aircraft A move in the straight line, 700 kilometer per hour go up, and 50 kilometer per hour square go here also. What does it mean? It means A accelerate, aircraft B slow down. Not slow, deaccelerate. Okay. So when you see this kind of question, you see collinear motion, recall back your chapter 1, chapter 2 circular collinear motion equation. You have your n, and t here, right? So coordinate axis. So you recall this equation. Okay, again, when you need to use this equation, when you see big X, big Y, small x, small y on the diagram, then memorize, apply. All right. B, because why? It asks you determine velocity of acceleration of A as measured by pilot B. So you this one, and this equation also you memorize. Modify accordingly. The question asks you about A. You modify your target. Answer is A. And your answer is from A from B. Change A from B. This is the standard. You change B stroke A to A stroke B. Same with this one. Same with the acceleration equation. Then use coordinate system to help you substitute inside there. VB, go up, positive J. Normal acceleration, V square over rho, because tangent direction. You get substitute answer. Rho was given 400 kilometer. So VB equal to normal plus tangent. You put in Vn is I. Okay, normal going in, right? 900 you calculate. Tangent was given minus 100 because it's pointing this way. This is omega, V over rho. Substitute, you get the clockwise direction omega. Clockwise direction is negative k. In this case, we work in hours. Normal unit SI is second, but this one you're given in kilometer per hour, so we'll work in hours. The rest you substitute also. Omega dot equal to A T divided by rho. Yeah, you see carefully. Velocity, omega, VB over rho. But omega dot equal to A divided by rho. Okay. You have all the answer, you substitute. So motion of A with respect to moving reference, RB stroke A stroke B equal to minus 4A. What about this one? You substitute inside. You substitute all this yellow color answer inside here. You have two equations. Solve simultaneous equation, you get answer. Okay. So at the end, you get your answer in minus I, positive J, kilometer per hour square. Okay, with this, we conclude chapter 5, right? So we will go into chapter 6 in our next lecture.